All right, today we're going to cover dynamics, and Newton's laws applies to that. In other words, situations where there's actual acceleration going on. It isn't often in physics that we can give you a straightforward recipe of things you have to do, or at least should do to solve problems, but this is one case where we can. This is what I like to call the Newton's law recipe, and it's a way to solve any force-related problem, although you have to follow it precisely, and it's often overkill. So we'll go through it, but you'll see there are steps that you really could have shortened or deleted, and that's fine. But if you're stuck, this skeleton will get you most of the way towards solving the problem. Step 1, read the problem. Step 2, for each object, draw a free body diagram. Step 3, write any constitutive equations from the problem. That means things that aren't necessarily Newton's law or that are always true, but in this case are known to be, like m equals 62 kilograms or something like that. That things that were given that you want to make connections of that aren't Newton's laws. For every object in each direction it can potentially move, find an expression for F net from your diagram. And find an expression for A, usually from the problem. Sometimes that's that A is 0 or A is G. Sometimes it's A is some number. Sometimes it's A is figured out from other kinematic quantities. But somehow find from the problem an expression for A. And then sixth step is write Newton's second law, which is always the same, that F net equals ma, for every F net in step 4, which is for every direction it can move. So every object for every direction. So if you have 2 objects and they can move in each of 2 dimensions, then you would have 4 such equations. Step 7 is substitute 4 and 5 into 6. In other words, replace F net with what you found in step 4, replace A with what you found in step 5. Then number 8 is sort of the most annoying, just solve. But I really mean just algebraically solve. All right, we're not talking about solving the physics problem anymore, we're talking about solving these equations, which are often mathematically annoying, but not usually overly challenging. And then step 9, reread the problem. As you know, often you can get so worked up in getting some result that you forget that it isn't the result you're looking for, and you should always check at the end and make sure. So let's apply this to various problems. Palo Alto Smith, famed archaeologist, is at the bottom of a cliff. He has his trusty bullwhip, which he knows can sustain a maximum tension of 950 newtons before it snaps. Palo Alto's mass is 62 kilograms, and we'll assume the whip is massless. To escape some pursuing Nazis, of course, Palo Alto uses the rope to accelerate upward as quickly as he can. Draw a free body diagram for him. Take a few seconds to sketch that out. We have our dot for Palo Alto. Of course, his weight pulls him down. And of course, the tension in the rope pulls him up. All right, he pulls himself up by pulling down on the rope, creating tension in it, which pulls it back the other way. We might want to also include that he's accelerating. That's not part of the free body diagram, but it's worth drawing, so we remember it. It would look something like this. Now I want to figure out what is the maximum upward acceleration in meters per second square that Palo Alto could safely have. And the factors from before were given, that the maximum tension is 950 and the mass is 62 kilograms. So we go through our recipe and we say 1, read the problem, which we've done. 2, draw a free body diagram, which we've done. 3, write constitutive equations. Well, for instance, one of those might be that the weight is just his mass times g. That's not a Newton's law, but it's true and it's useful, and we'll find in a minute that it's very, very helpful. Step 4 says, from your diagram, find expressions for F net. So I go over here, there's only one object, which is Palo Alto, and there's only one direction, which is vertically. So I only have one F net, which is nice. All right, I might say F net Y, but there's only one of them. And from the diagram, it's Ft minus Fg. Why minus Ft? Well, it's Ft vector plus Fg vector, but Ft points up and Fg points down, so we know they come with opposite signs. From the step 5 says, from the problem, find an expression for A. And here we're just going to say that the acceleration is just what we're looking for. It's kind of a silly statement. I just do it to make everything fit that recipe. That the acceleration I'm looking for is some value A0, which is what I'd like to find. Now remember that step 6 is that F net, F net equals ma. And I'm going to take the stuff from here and substitute for F net, which gives me Ft minus Fg. And I'm going to take the stuff from here and substitute for A. And what I'm looking for is A0. So let's get ourselves some more working space. And we have that A0 is ft minus fg over m, which is actually ft minus mg over m. And I'm going to do a little bit more stupid algebra. You could just get numbers at this point, but I'm going to do this because I can write this as ft over m minus mg over m. And that way I just get 950 kilograms over 62, sorry, 950 newtons, should get the units right, over 62 kilograms minus 9.8 meters per second square, which has a value of 5.5 meters per second square. So that's the quickest that Pally can climb this rope without it breaking. Quickest acceleration you can have. Now, if there were a steady and significant horizontal wind blowing, what effect would that have on your answer? So when you think about that for a second, that would change our free body diagram, of course. Now it would look like this. We'd still have his weight pulling down, but then we'd have some force from the wind pushing him over that way, which means that in fact the whip would have to point at some angle. And that means that in this case we'd have that FTY, the vertical component of the tension, would have to balance out gravity. But then that number FTY has to be less than FT, because it's the leg of a triangle in which FT is the hypotenuse. And so, right, we have FTY, FTX, FT. So we have less leeway, so our acceleration would be less, which makes sense. You'd have to climb more carefully if there was a wind. All right, Palo Alto climbs to the top, but sometimes later he needs to descend again rapidly, but he's misplaced his whip. There is a rope he can use, but its maximum tension only 450. There is no wind. What is his minimum downward acceleration such that the rope does not break? Take, I don't know, a minute or so, stop the video, solve the problem, come back. Again, step 1 was read the problem. Step 2 is let's draw our free body diagram. Oops. We have basically the same diagram. His weight downward. He's supporting himself on the tension upward. Now there is a downward acceleration, which I'll call A1. Step 3 says give us any constituent equations. So Fg is still m times g. And although I didn't write before, I can also say that Ft is less than or equal to 450 newtons. That's a constitutive equation also from our problem. Step 4 says find an expression for Fnet. So Fnet from our diagram. And we see that from our diagram it still looks like Ft and Fg, but a minus sign because Fg is downward. And then find an expression for A. And here I say, well, I'm accelerating at rate A1 that I'm looking for, but I want to be careful because I've now chosen, right, since Ft was positive and Fg is negative, upward is positive, my vector is downward, I have to remember to also put a minus sign here. So you need to be careful that you get all your things lined up. You might find it more convenient, and some do, to always make the acceleration the positive direction, in which case just be careful writing your force equations. It won't matter, but it might be a little easier algebraically. All right, step 6 says write F net equals ma. That one's easy. And then step 7 says substitute and solve. So we end up having Ft minus Fg, and that equals the mass times minus A1. And then we solve again for A1. Notice we've picked up a minus sign over here so that when we do our arithmetic and so on, we're going to end up with an expression that says that A1, oops, that's pretty bad A1 is Fg minus Ft over M, or Mg minus Ft over M, or now it's G minus Ft over M, or 9.8 meters per second square, minus, remember that our max value now is 450, not 950. But his mass is still 62, and we get 2.5 meters per second square. This is the minimum acceleration, which is weird, right? But this is the least he can have. We can show that formally, and I think I will as an aside on the next screen, but just keep in mind, the idea is that if he goes slower than that, then the rope has to pick counter more of his weight, so it would be over the 450 newtons. If you didn't like that informal reasoning, then here is a slightly more formal proof. And what I'm going to do is I'm going to solve for Ft instead of for A. Now I'm going to get that Ft is Fg minus Ma1. But we also know that Ft is less than or equal to 450 newtons. So Fg minus Ma1 is less than or equal to 450 newtons, which means Fg minus 450 newtons is less than or equal to Ma1. And now we can do the same sort of thing. Fg minus 450 over M is less than or equal to A1, or A1 is more than, and we get here again, Mg minus Mg over M minus 450 over M, or A1 is greater than 2.5 meters per second square. But we've seen where the greater than sign came from mathematically. It comes from the fact that the tension has to stay low. That's actually what's controlling it. All right, a rope is attached to a 50 Newton ball suspended from a wire and pulled horizontally until the wire makes a 20-degree angle. Then the rope is held so that the ball does not move any further. What is the tension in the rope? Well, step 2, remember, is to draw our free body diagram. And we have, of course, the weight pulling down. And we have the tension of one thing pulled here, which I might call Ft. Actually, I'm going to change that in the sense that we're going to have both wires and ropes with both have tensions. I'm going to call this the force in the wire. And then we'll have the rope pulling this way, and we'll have the force of the rope. And that way we avoid which tension do we mean when we say the tension, because we don't have to. All right, step 3 says write constitutive equations. One that we're going to keep doing over and over again is this. Although here we were given that this is 50 newtons, so maybe we won't need the mg part. Step 4 says find an expression for F net from the diagram. Well, that's pretty easy. F net equals Fr plus Fg plus Fw. Why aren't there any minus signs at this point? Because I'm using the vectors, so those already include the directions. Remember, the minus sign comes from putting the direction of the arrow in, and I put the direction in by saying I'm talking about their vectors. Why did I do that? Because F net will be their sum, but we also have step 5, find an expression for A, and they say it doesn't move any further, so A is 0. So this is not really a dynamics problem, it's really a statics problem, and that makes life really easy because we know that step 6 says F net equals MA, which means it equals 0, which means I have 3 vectors I can just add. So I can just say Fg downward plus Fr over plus Fw upward at that angle is a right triangle. And I can start putting in things on my right triangle. I know, actually I'm going to draw that triangle a little larger, since it's going to be our main solution thing. So let me draw it much larger. Fg downward, Fr over, and Fw back. And I know things. For instance, I know that Fg is 50 newtons. Is 18 newtons. 18.2 really, but 18 newtons. That was pretty quick because we could take advantage of the triangle geometry. Another way to have done this would have been to take the components, but then we'd have to solve for FW, which I don't want and don't need, and don't have, and so I wanted to avoid that. All right, sometimes problems are multi-part. They use multiple things, like this. A sled with a mass of 20 kilograms slides along frictionless ice at 4.5 meters per second. It then crosses a rough patch of snow that exerts a frictional force of 12 newtons. How far does it slide on the snow before coming to rest? Let's draw a picture way back to our early days in physics. Here's our picture. Here's the sled. It's really more like a toboggan, but that's okay. It's moving with some velocity of 4.5, but then it encounters roughness and gets slowed down, so there's an acceleration which points that way. I'm going to call it A0. I don't know A0, but I can find it by doing a free body diagram. What are the forces acting? Well, there's the weight and the normal and the frictional force, but we know it's along level, at least applied here, it's along level ground, and so therefore the normal and the weight will cancel out, and all I have is FF. We know that F net equals MA, and we have here that A is minus A0. So we have something like minus FF, because it's pointing in the opposite direction, equals M times minus A0. Or the acceleration is FF over M, which is 12 newtons, 20 kilograms, or 0.6 meters per second square. Notice I found the magnitude of the acceleration. Now, it's a kinematics problem. Now we're saying if I have my sled and it starts at 4.5, but accelerates this way at 0.6 meters per second square. Let's find the distance it travels. So I'll say here it starts at the origin, but ends at the distance I'm looking for. It has an initial velocity of 4.5 meters per second and ends at 0. And of course, there's the time. Starts at t equals 0, ends at some unknown time. I don't want that. What I wanted was this. So I look here and I say, well, I have two distances. I have a velocity and acceleration. I don't have time. I don't want time. We're going to use the vf square equals v0 square plus 2 times the acceleration times the change in position. We end at 0 meters per second. We start, at 4.5 meters per second, and we square that quantity. And then we add in twice. Our acceleration, remember, is 0.6, but with a minus sign because it's going the other way. And then finally we have the distance. And we can solve for that. So we can say that the distance would be, bringing all this stuff over, 4.5 meters per second quantity squared over 2 times 0.6 meters per second square, where the minus sign has been taken care of because we used it to move to this side and then divide out. And we end up with 16.9 meters, something like that. This wasn't a very difficult problem, but I want to point out that you might start seeing kinematics problems where you first have to do a force problem. Or you might do force problems where you'll need an acceleration from a kinematics problem. In other words, the Unit 1 stuff doesn't go away. It actually continues throughout the whole class. And if you're uncomfortable with it, it's time to really practice it and get okay with it.